We've learned a lot of formulas this term so far, but a lot of them have been based on previous formulas. This topic is no exception. Remember these two formulas? The sine of the sum of two angles and the sine of the difference of two angles? Let's take a look and see what happens if we combine those. If I take the sine of a plus b and add the sine of a minus b, that has to be equal to sine A cosine B plus sine B cosine A. That's this one. The sine of A plus B is equal to this expression, and that's based on this formula we have here. Now I'm going to add sine of A minus B, and that's based on this expression here. So I'll have plus sine A cosine B minus sine B cosine A. However, notice that, try to use a different color here. Notice that I have a sine A cosine B here and a sine A cosine B here. And then I have a sine B cosine A there, but I have a minus sine B cosine A here. So those cancel out, and the sine A cosine B's can be combined. I have two sine A cosine B. And that's clearly still equal to the sine of A plus B plus the sine of A minus B. And then if I divide both sides by 2, I get, and I'm going to write this term over here, sine A cosine B equals 1/2 the sine of A plus B plus the sine of A minus B. And this is what we call a product to sum formula. I've taken the product of two trigonometric functions, sine and cosine, different angles, and I've changed it into the sum of two trigonometric functions, sine and a sine, with different angles. A plus b is going to be a different value than a minus b. I can do the same thing with the cosine of a plus b and the cosine of a minus b and combinations of those, and I'll end up with the following three formulas, in addition to this first one. Notice that all four of these are either the sine or the cosine of angle A and angle B, and the left-hand side here is a product. So, for example, here I have sine A cosine B, and down here I have cosine A sine B. Yes, I could also have written this as sine B cosine A, but this way all my A's are aligned and all my B's are aligned. So this one's sine A cosine B, this one's sine B cosine A. Then I have the product of two cosines, cosine of A and cosine of B, and the product of two sines. On the right-hand side, every single one of these is made up of a sine of an A plus B and a sine of an A minus B. Every other one is a plus, every other one is a minus. And if you take this piece of the formula and play around with it, you end up with the entire formula. That's actually how we got this first formula. We started with sine of A plus B plus sine of A minus B. We rewrote what those expressions were, how they could be simplified using the formulas. The sine of A plus B is this, the sine of A minus B is this. We rewrote those, and then we played around with them until we had solved for this product. If you do that with each of the insides of the following three, the additional three formulas that we've come up with, write these out, expand them using the formulas, and then solve for the product, you end up with the other three formulas. So rather than do that for all four formulas, I've done it for one, and I've explained how to do it with the other three. But I don't think we need to take the time to actually derive all four of these formulas. Instead, let's use our time to look at an example. I'm going to leave our four formulas where we can see them and access them easily. And then let's take a look at this example. Rewrite as the sum or difference of trigonometric functions this expression here, 10 times the sine of 37x times the cosine of 24x. Let's start by identifying this 37x as my a and 24x as my b. In fact, I think what I'll do is write a above 37x and b above 24x. Now, I have a formula for the sine, ignore the 10 for the moment, the sine of a times the cosine of b. It's this expression right here. So I'm going to rewrite this as being equal to 10 times 1/2 of the sine of a, which is 37x, plus b, which is 24x, plus the sine of a, which is 37x, minus b, which is 24x. And then I can simplify. This product here gives me 5, and then I have the sine of 37x plus 24x is 61x, plus the sine of 37x minus 24x is 13x. And there's my answer. I could, if I wanted to, write this as 5 times the sine of 61x plus 5 times the sine of 13x, but we're not really sure how we're going to use this, so either of those would be correct. Either this form of the answer or this form. But that's pretty much it. The thing you have to watch out for is leading coefficients that may or may not be even numbers, so this might not actually divide into a whole number, and making sure you do your arithmetic right. You also need to make sure you're using the correct formula. This one's a little tricky to identify because if I rewrote this as sine b cosine a, then on the left-hand side it looks exactly like my first formula here, except that my a and my b are the opposite angles that they are here. So that means a and b over here get switched as well. So I could rewrite this expression, let's do it this way, this formula here can also be written as the sine of b times the cosine of a is equal to 1/2 the sine of b plus a. No change there because addition is commutative. So we get the same answer for b plus a as we did for a plus b. Then I'm going to subtract the sine of b minus a. Now I get a different number. A minus b and b minus a have the same numerical value, but they're opposite each other. Sine is an odd function, so if the negative in here throws a negative out here, then that changes that sign as well, which gives me the same formula as I had up here. Pretty cool. This is just a version of this formula. Why don't you check and see if this formula here is just a version of this one? My point here really though is to make sure you're using the right formula, and if you end up using a different version of that formula, then make sure all your arithmetic and algebra is correct as well. Now your textbook has been calling these product to sum formulas, and in fact that's what this particular part of this video is about. I'm going to take a product and turn it into a sum or a difference. You could argue though that you could also call these sum to product formulas. If I have a sum, I can interpret it as a product. As with a lot of the work that we've done in this chapter, this section on identities and analytical trigonometry, I can simplify the formula for going from a sum to a product by doing a little bit of algebra. So let's do that next. To start with, remember that how we got this first formula was to say that the sine of a plus b plus the sine of a minus b must necessarily, because of what each one of these is equal to, must necessarily be equal to this. Sine a cosine b plus sine b cosine a plus sine a cosine b minus sine b cosine a. And that sine b cosine a and negative sine b cosine a cancel, leaving us with 2 sine a cosine b. After that, I divided both sides of my equation, my new equation, by 2. But what if I didn't do that? What if instead I did a substitution? Let's let u equal a plus b and v equal a minus b. Then I have the sine of u plus the sine of v on this side. And now I have to figure out how to write a and b in terms of u and v. If I take my substitution equations and add them together, I get u plus v equals 2a plus 0b. That means that a is equal to u plus v over 2, or well, I guess I'll just write it that way, u plus v over 2. So on my right-hand side now I'm going to have equals 2 times the sine of u plus v over 2 times the cosine of, well, I need to figure out how to write b. What if I took this pair of equations again and wrote them as u equals a plus b and negated the second one? So this is going to be negative v equals negative a plus b. Negative v equals negative a plus b. That lets me cancel the a's when I add these together, but I get u minus v equals 0a plus 2b. That means that b is equal to u minus v over 2. And now I have a formula for taking a sum of two sines, the sine of one angle plus the sine of another angle, and writing it as the product of some sines and cosines. If I know u and v, I can add them together and subtract them and get the things that I would need to plug in here, which means I can write the sum of two sines as a product. Again, I could work through this for all four of these formulas, but rather than bore you with the details of all four, because the demonstrations are really pretty similar, I've demonstrated one, this first one, and I'll just give you the other three. These are called sum to product formulas. We have four of those, and we go back up here to the top right-hand corner. This is a review of our product to sum formulas. We've already talked about these ones, and I've done one example of how to use a product to sum formula. So let me do an example of how to use a sum to product formula as well. I think what I'll do is erase this corner and do my example here. We want to rewrite a sum or difference of two functions as a product of functions. We're given a difference of two cosines. So let's recognize first that this is my a, or my u, I guess, and this is my v, u and v. Now, you can write all of these functions using a and b instead of u and v, or x and y for that matter. And you can write them so that they use the same letters, a and b, u and v, or x and y for these formulas as well, the product to sum formulas. The reason these formulas in the bottom left-hand corner use a different set of input variables, u and v, is because I did a substitution and I replaced a plus b with u and a minus b with v. But now that we know the formula, we can say this is an a and this is a b, as long as we also say this is an a and this is a b, and this is an a and this is a b. So it doesn't matter whether you call your variables u and v or a and b or x and y. Now, how are we going to name our variables? Well, since my current screen shows the variables as being u and v, I think I'll do that here as well. I'll call this u and this v. The formula that I have for that is the difference of two cosines, and that's this last one down here. A cosine of u minus a cosine of v is equal to negative 2 times the sine of u plus v. That's going to be 24.8t plus 6.8t all over 2 times the sine of the difference of those two, 24.8t minus 6.8t all over 2, which equals negative 2 times the sine of, now the rest is arithmetic and simplification. 24.8 plus 6.8 is 31.6, so I get 31.6t over 2 times the sine, 24.8 minus 6.8 is 18. I get 18 over 2. And then my last step will be to reduce these expressions inside the parentheses. 31.6 divided by 2 is, so I'm going to get negative 2, the sine of 31.62 times the sine of 9. And this, I'm sorry, I ran out of room again. That's so typical for me. This is my final answer, recognizing that this is a product, 2 times the sine times the sine. Now, the reason I chose this formula to work with, this example to show you, is because it's the only one with a negative in it. There's a negative in front of the expression, so it's very important to include that negative in your answer if the problem that you're given is a difference of 2 cosines. Other than that, it's fairly straightforward. You identify your A and B or your U and V, you plug them in to your formula, to your right-hand side. Don't forget your negative. Don't forget your 2 for that matter. And then you simplify. The last step that I did here was to simplify this expression because 31.6 over 2, while a valid number, is neither a decimal nor a fraction. It's kind of both, but not really either one. So polite mathematics means simplifying that into either a decimal or into a fraction. I could have changed that to the reduced fraction equivalent, but that's 1,581 divided by 50. So in this case, since we were given decimals, it's better to use decimals anyway in our answer. So there's my decimal answer. All right, well, that pretty much covers it, not just for this topic, but for this section. We're now finished talking about the double angle, half angle, and product sum formulas. The next thing we're going to do in this course is talk about how to use these formulas, all the formulas and identities that we've learned so far, to solve basic trigonometric equations.